Hey, what's up everyone? Thank you for joining FP 101 again. We're going to be talking today about functors, and we're going to branch off of that or extend upon that concept and talk about bifunctors and profunctors. But to take a step back, what is a functor? A functor is something that allows you to map over what's inside of it. So it's any context with a mappable interface. So you can think of an array in JavaScript where you provide a function within map, and what that would do is on every element that you iterate over in the collection, you're going to be transforming the element with this function from A to B. And when I say A to B, I'm just speaking about generics, where it could be an array of strings, and each one you're going to turn into a number based off the length of the string. Or it could be an array of strings and you want to map over each string to a new string, where for instance you might uppercase each element. So this is going to make more sense whenever we start to look at code and the slides that I have prepared, but we're going to start with the basics and grow upon or build upon each concept as we go along. Now, to provide you a little context about the format of this episode before we dive into it, we're going to start theoretical and just talk at a high level as to what these things offer, and then we'll look at some code examples, we'll look at some type signatures, and hopefully this will help drive home the point of what these things are, when you might want to reach out to them, so forth and so on. Okay, so as mentioned, what we're going to be looking at here are functors, which give you this map method, and a bifunctor, which gives you bimap respectively, and then profunctor gives you promap. Now, before we dive into that, I want to give credit where it's due and let you know that this video was inspired by this article written by Tom Harding, who's a software engineer who has an amazing series, this blog series on different functional programming concepts. Now, in his article, you'll see, and actually all of them, he has Haskell signatures, which kind of show you what's going on at a type level. And then the actual implementation is done in vanilla JavaScript. And I believe he's using this library called Daggy, which allows you to build up certain type classes and algebraic data types and then use them. But what we're going to be using, as you might have guessed, is FPTS. So this is going to be an implementation of the same concepts using FPTS, and talking through these things in TypeScript for you. Okay, so back over into our diagram over here. So we make our way down. We're going to see a difference here between functors, bifunctors, and profunctors. And that is that functors and bifunctors are covariant functors, and a profunctor is a contravariant functor. In a nutshell, you could say that covariant functors map over the output of something, where contravariant has the ability to map over the input. So let's take a look at what that means. As we mentioned before, with a regular map, you could be going from a string to a number or a string to a string. So whenever I'm mapping over each element, like I mentioned before, I could have a string that I'm taking the length of and therefore converting it into a number. And one thing to call out here is you'll see these capital letters inside of our examples and inside of these type signatures, and you'll also see lowercase letters. And I want to call out real quick the difference between those. So this is a good way, or a good intuition, I think, that will help explain. So we've already covered what an option algebraic data type is. It can either be a none or a sum. And you'll see this capital A gets piped through to the sum of A if the value within the option is present. And the capital A just means that it's generic, right? So this is parametric polymorphism, in that this could be an option of a string, it could be an option of a number, or it could be an option of a Boolean value. Not that that would be common, but the point of the matter is that the capital letters are for referencing generics, whereas lowercase letters are for referencing values. So if we come down here and we just check out this isSum function, in a nutshell, you could say that we're making sure that the value, f of a, is a sum. All right, so that's it for that. Now, moving our way back down, so we've talked about covariant for our regular map, Now we're going to look at covariant for a bimap. So previously I've made a video for going over either. And either is an ADT that can either have a left value inside of it or a right value inside of it. And the example that we use to demonstrate where that ADT is useful is for form validation, where you either have a validated form or you have a invalid form. And what bimap will allow you to do is provide a mapping function to both of those channels. So algebraic data types, it's an abstraction or a context that abstracts over all possible states within that context. So whereas with option, you can either have a value or there is no value, and with either, you either have a successful value or an error value. Now, you don't have to use it like that with either, but convention dictates that your left channel is for the error case and your right channel is for the success case. Whenever you're inside of the context, you can map over the right value. So if you have a successful value, we want to do this mapping operation. But if we have an error, maybe we want to provide a mapping function that will also map over that. And this will make it more sense whenever we look at the code. Now, making our way down, we also have contravariant. So with the promap here, you supply it what's known as a contramap, and that is where you actually map over the input. And then you have a regular map supplied as well, which maps over the output. Don't worry if this is the first time you're ever hearing about contramap. I'm going to walk you through an example of that as well so that you can see what that is. Okay, so here is our basic application. This is the entry point anyways. And you can see that I have different examples here that I'm going to walk you through. So we have a map example, we have bimap, we have contramap, and then we have profunctor. And I'm going to uncomment each one after I walk you through the code and show you what that looks like. But this is a very simple application which looks like this at the moment. You could see hello friend. If I actually come in here and put that back, then you should be able to see, yeah, my name is Elliot down at the bottom. Okay, so let's go ahead and look at what's going on in the map example. So what we have is we have a use state that has an option of a string. Now, we've already mentioned what an option is. It is either a none or a sum. And the A here, the capital A, is a string that we're passing through. So that generic is being supplied to this interface or this type. And right here we have a sum Elliot, which down here we say, okay, we know that we have an option of sum. And if there's a value in there, we're going to go ahead and perform our mapping operation. So if we do have a name, we know that is a string, and we'll uppercase that name. So basically, we're just going to shout it. And this O dot to nullable, all that this is doing, see if you can see it right here. Basically, if we match over what's available in here, we say, hey, if nothing was supplied, then we're going to say it's null. Otherwise, we have a name, and we'll just return it. So if I save this and I go back to my example, you'll see that my name is Elliot, still renders. So it's doing the same exact thing, it's just shorthand. So we say, hey, go ahead and unwrap it, and if the value is not there, just dump it out to null. And in React, as you know, if you don't have anything, then nothing will render. Or sorry, if you have a null present in your JSX tree, then nothing will render. So if I change this to no value, which you can see up here is o.none, we'll go ahead and save that, and then we'll come back to our example, and you see that it's gone. Okay, so let's move that back on to sum. Now, before I move on, I just want to take the time to explain that this was one of the things that was, I wouldn't say difficult, it just took a little bit of time for me to wrap my head around in terms of a mapping operation that wasn't mapping over a collection of items. because as a JavaScript dev, before you enter FP land, that's sort of all you know, right? Is that you can map over an array, or you can reduce a collection. You can do the same for an object where you might map over the entries and, you might iterate over the entries of an object and then map over those things. But really what you want to know about is that functor implementation, right? Because that's what allows you to map over things in an array. But the same is true to other data structures as well. You just may not be aware of it at the time because you've only worked with array. And that was me. So whenever I was looking at option and I'm looking at either, I see that in their modules within FPTS, which is what we're pulling in here, you have map functions that are methods, if you will, that are defined within these modules because it's an implementation of the functor. So one thing to note here is that only if you have a value will this run. If not, it'll drop straight through, it'll short circuit and go down to where you're unfolding. So name option here is just going to check if it has a value or if it doesn't, and if it does, then we're going to go ahead and do that thing that we want to do. This is more declarative because you're just telling the computer or you're telling your application, look, I don't care like what instructions you want to take to get to the result, but this is how I want the result to look. So you're declaratively saying how you want to transform the values, and it allows you to code along the happy path. All right, now we're going to move on to the Bimap example. So over here, we're going to start by identifying what state we're iterating over. And you can see that if I go here, there it is. We either have a number or we have a string. Now, as I mentioned before, usually your right channel is for the success, which in this case would be a number, and your left case is for an error, which in this case would be a string. And we start up top, we have both the right and the left value already determined. Now again, this is all contrived examples, so you're not going to pull this into your production application as is. This is just to help you understand what these concepts introduce. All right, so we're going to start with a right value, and we're going to declaratively map over both of these success channels and error channels with Bimap. So we start with a form validation, which is in either instance, and here we supply both mapping operations at the same time. Now this doesn't mean that it's going to run concurrently. We're just saying that, hey, we already know if we get back an error, we want to map over that. Or if we get a success, we want to map over that as well. So here are both functions, and you decide whichever value gets passed through here, which operation to run. And then ultimately what we'll do is we'll match over the state that exists. If you've been following my series previously, this e.match would have been known as e.fold, and that still exists within the library, but it's being deprecated. And to give you a brief explanation, .fold or fold for a function is kind of an overloaded term because depending upon where you're using it, it could do different things. So I believe Jacanti, the author of FPTS, has renamed it to match because it's a bit more intuitive, because really what you're doing at this level is pattern matching. You're matching on the state that is explicitly being operated over at that time. So this is a beautiful thing about using these data structures, is that it allows you to explicitly handle the states that exist. So I'm sure you've heard a lot about state machines and finite state machines. You can think of these data structures as using finite state machines within your application and within your code, and at the level of manipulating the data, such that you're always making sure that you kind of force your logic into these channels or into these states so that everything is accounted for. All right, now back to our example. Whenever we match over the operation, so here we have our mapping values, where we're going to map over the left channel and then the right channel, and then now we're going to go ahead and match over what exists there. So if I show you right here, if I just do this identity function where I pass back the same thing and I hover over it, you can see at this level we have an either, as we expect, of string or number. So we go ahead and get rid of that. And you can see here we have an error message. This is what I'm calling it, error message. You could call it whatever you want. And it has a value of string. So we're going to pull that out and say whatever we want to the application. This is where we want to handle. This is where we want to handle our error logic. And then right here, we're in the right channel, and what we want to do is just go ahead and show the user a successful form or a validated form. Now, I'm using this pattern within my JSX, so within what's returned and what's going to be rendered. And if I save this, we'll go ahead and take a look at what gets rendered. I think I have to go ahead and uncomment the next thing as well, just so that it bumps it up high enough. Okay, yeah. You'll see right here we have a validated form with the value 12. And why is it 12? Well, we started off with 6 as our value right here. And in the mapping on a successful channel, we multiplied it by 2. So if we go ahead and now change this from a right value to a left value, you would expect that invalid form should be uppercased. And then whenever we match over that, we're going to return this bit, this portion, instead of the validated form. So it'll just take that uppercase message and dump it out right here. So if we come back, yes, you can see that is exactly what happened. Cool. So this is by mapping in a nutshell. Now before I move on, let me go ahead and let's go ahead and comment this out. I just want to show you. So right here we could do our map where we say, hey, if we have a number, then let's go ahead and do the same thing that we were doing before, right? We have a right value, so we know that in this instance this operation will run. So if we come back, you can see that it is running how we expect. And what we could also do is say e.mapLeft, which, as you would imagine, is going to be our error message. We'll just call it that. And what we're doing to uppercase. Okay. So let's go back real quick. We haven't changed, it's still a right. So we haven't changed that. We come back over here, just refresh to make sure. You see what happened? It jumped over this because this is only going to operate on the left channel, whereas this is only going to operate on the right channel. So if we come back over here and we say, hey, actually we're starting off with the left value. So imagine we have an invalid form. So now what's going to happen is this should run and then this gets skipped. Yep, so you can see that's exactly what happened. So we come back to our code. You can see that this handles both of these cases in one step. So we can get rid of that, supply them both at the same time, and presto, you have a bifunctor implementation via the bi. Okay, now before we move on to Profunctor, we're going to take a slight deviation and talk about Contramap. So back over here, we said that for covariant functors, you have the ability to map over the input. And in promap, which is a method that belongs to Profunctor, you have the ability to supply both the input mapping and the output mapping. So you have a contramap step and then you have a regular map step. So really nested inside of promap, you have a contravariant functor and a covariant functor. So we'll go ahead and take a look now at what contramapping is. So we'll bring this back up, and what we're going to be looking at is this bit. Whoa. Okay. So with contramapping, let's start up here. We have an interface of a user profile, which has a handle, an email, and a created at. Your created at is a string. So imagine in your database, you save your dates as a string, which is super common, especially depending upon the database that you're using, whether it's MySQL, Postgres, what have you. Okay, and we have this pluck date from profile, where it's actually using a contramap. So before I cover what's going on here, let's just keep walking through the code for a second. So let's start maybe down here with what's being returned in the JSX. And I'm gonna bump this out a little bit so that hopefully, yeah, you can see everything all in one place on the screen. All right, so at the top we have unsorted profiles, which is just going to show you the collection of our profiles. And then you have sorted profiles. And then you have that function up there that I showed you, which has which I skimmed over. There's a function defined that says sorted profiles by date created. So it takes in an array of profiles and it gives you back an array of profiles as well. But this time sorted, and it's sorted by the date it was created from, I believe, the oldest to the latest. I mean, yeah, oldest to recent. And we'll take a look at that. All right, so I'm gonna bump this back up, and now let's go at the top. So here's our state that we're gonna be operating over. We have a bunch of user profiles. Each of them have a handle, email, and created at. And just as I mentioned, all of these are strings. And what we want to do is this bit right here. This is the important part. Or here's the function, sorry, that we were looking at earlier. So you pass in an array of profiles, and then we're going to pipe. So as I mentioned in one of my videos before, piping is just left to right composition. So we start with an array, and then that result gets piped into this result. Let me call this excess. It makes more sense. But because of point-free composition, we don't have to do this. So you can see right here, this is a curried function. So first it takes a ORD instance, and then it's expecting the actual collection that you're going to map over. All right, so I can get rid of that because of point-free composition. Makes our code a bit more concise. All right, so let's take a look at this. So pluck date from profile is going to give us back an ORD instance. And let's look at how that happens. All right, so pluck date from profile takes in, we start here with this D is being imported from FPTS, and I'm aliasing the date module. So the date module has an ORD instance on it, and here's where we get to use our fancy contramap. So this is our before hook. Before we go and sort through this entire collection, what we want to do at each level is pluck out the date, and we want to sort by that. So because I have this this ORD instance, I can supply this ORD contramap, which says, hey, given a user profile, go ahead and pluck out the date created at, and we're going to pass that through the JavaScript function to actually create a date. And this guy right here knows to take that, so this date ORD instance knows to take those dates, and it knows how to order them. So if we actually look at what comes back from this, as you can see, it's an ORD of user profile. You can see that we have a couple methods available to us. We can compare, or we can see if things are equal. So let's just take a look at this compare, because that's what this sort cares about. And I'm going to show you the actual implementation of this in Jaconti's source code. So if I come back over here, let's jump, I think it's right here. Yes. Let me bring this into view. So as you could see up here, this is being imported from the read-only module, read-only array, where you have this sort function or sort method implemented. And what it does is, first it takes an ORed instance, and then it takes an array of values, and then it does this quick little ternary where it says, if you only have one element, just give me back the collection as is, because there's nothing to sort here. Otherwise, it will slice up that array, which is essentially creating a copy, and then it'll sort by. Now, these are native functions inside of JavaScript's implementation of the array prototype, and you could see that here in MDM docs, where if you don't provide any ranges of where to start and end, it just creates a copy, so that we're not mutating over the original array that was supplied. And then sort, you can see, has this cool thing where you supply it a comparator. You can supply it a comparative function, and then it knows how to sort the collection that you're providing it. All right, so if we go back over here, what it does, again in a nutshell, is you give it that ORed instance so that right here it knows how to run the compare and creates a copy of the array, and then it sorts them all by the comparator supplied. So if we jump back over here, again, because this is now an ORed instance, it has that compare function inside. So it's all smart enough to infer those things and understand exactly how things should be sorted. So right here, whenever it gets applied, it knows to go and do its magic. But again, what's really cool about this is the Contramap step. So up here, this runs before the sort runs. So you have the profiles that come in, and before we map over the output, which in this instance is just an A to a B, but it's a string to a string. We're not doing anything different, right? What we're doing is we're first telling it, we're informing it how to transform the input that's coming in to the sorting function, such that we get back this ORed instance, which has a compare method on it, which could then be supplied to a.sort. So ultimately, what you end up with down here is the function, which takes in the same thing that we're mapping over up top, or that we're stringifying in this JSX right here. So it's taken in that, and then it's actually sorting on them. So if we jump back over here, you can see the output of what that looks like right here. So we start with, let me zoom out a little bit. I'm gonna zoom way out. Okay, so we start with unsorted profiles, and you can see we have hello first, hi, and then yo, or foo bar bars. And first we have unsorted profiles, and then you could see that they've been sorted since. And like I mentioned before, it's being sorted by the oldest to the latest, or to the most recent. Okay, and now we are on to the last example, which is a profunctor. So if we come back over here, we just covered the contra mapping step, where we talked about how you can map over the input of something. And a profunctor gives you this promap method on it, which allows you to supply that contra map step and the regular mapping step for the output at the same time. So think back of how we did this piece before, where we supplied two different functions at the same time. Promap is going to do the same thing, but for the input and the output. However, the difference here is that with the bifunctor for either, it would only run each function supplied dependent upon the state that got piped into it. So if it was a left value, it would run the on left, and if it was a right value, it would run the other function. The difference here with promap is that regardless, what's going to happen is both of these functions are going to be run, because you're transforming the input and then you're transforming the output. So we'll go ahead and take a look at that example. So without a doubt, Profunctor is definitely more advanced. So let me go ahead and back this out a little bit. There we go. So we're starting with the same interface, which is just user profile, handle, email, created at. They're all strings. And this is what the type signature actually looks like for a promap. Let me see if I back this out one more. Yeah, I think you could see everything. I'm going to squeeze this back in though, because this might be too hard to see. Maybe what I'll do is just break this up on a new line. Okay. So what's happening here with promap is that you have 4 different generics that are supplied. You have the 2 functions that are supplied up front. So this promap gets partially applied with your contramap step and then your regular mapping step. So you have an F, which takes a D to an E, and then you have a G, which takes an A to a B. And right here, the next thing that it takes, now this is curried, right? So you partially apply it with this. And we're using the reader implementation, or sorry, the promap from the reader implementation to explain this concept. So you take the partially applied contramap and regular map, and then you have this reader, which is another function. A reader is basically just an R to an A, or an environment to an A. So you have a function of something, think profile, and you want to map over to maybe just the maybe like one value within that profile. All right, so you have an F of A, and then ultimately what you get back from that process is a reader. So this is how it looks in a nutshell. So you have an A that comes in, and then it first runs that contramap, and then it runs the this portion right here, the F of E to A, and then finally it runs the results of all that on the G. Now trust me, I know that this is hard to follow. We're going to keep walking through it, and this may require you to come back and look at it again, but know that all of this code is going to be accessible to you on my Git repo. I've also created a code sandbox for this video as well. So I wanted to minimize as much of the friction as possible just to get people in and get their hands dirty if they wanted to play around and tinker with this further. Okay, so we're pulling off a promap that exists on the reader instance, and no different than the other examples, we have a foo user profile here, and we have this function. So let me go ahead and scroll this into view. Here's where we're going to bring everything together. So I'm actually going to pull this down over here so that we can see this all on the same screen. Right. Pull this over. Okay. Okay, so what's happening? So we start off with the config. In this instance, it's just foo. So what we looked at up here, you have foo's information, which is just handle, email, created at. All right, and now we want to promap off of that config that was supplied. This should actually probably just be called a profile. Okay, so we have a profile that was provided, and we're going to partially apply our promap with our contramap step, which is this portion right here. You have the F of D to E, and then you have your output. So here's our contramap, and then here's our regular map. Here's our contravariant functor. Here's our regular covariant functor. So let me highlight this so that it also highlights it above. So you have this step, which actually runs first, and then you have this step, which runs last. Now in between those steps, you have your F of E. So remember, whenever you're looking at function composition, regular function composition, it works its way from the inside out, just like regular math. What we're doing here is left to right composition. So we're saying, hey, we're going to start with this thing. We're going to partially apply our promap, and then we're going to run this thing in between. And then in the end, we're doing this identity. You saw me do that before, which is just this. These two are literally the same thing, and it's actually a pretty common operation to use sometimes, so it's been aliased as identity, and you can import that, or sorry, you can import that from FPTS. Okay, so what happens here? So let's walk through this again, and we'll walk through it slowly. So we have a user profile, which has this information in it, and then what we want to do is we say this portion right here. So we say, given that we have a user profile, we want to take that profile's handle and turn that string into a number. We're going to pull off the length, because what we want to do here is just check that like the handle is long enough. So to draw this back to like a real world example, imagine you're trying to create an Xbox handle or a PS5 handle for the network, right? You want to go online, play with your friends. They have their own validation mechanism for making sure that it's of a certain length, or that it should be of a certain length. And a lot of times it's like, make sure that it's no longer than this. But anyways, so here's our reader, where we're taking this configuration object and we're plucking out one specific thing. In this instance, it's the handle. And like I said, we're taking the string and converting it into a number. So before we do that, we actually run the contramap step, right? Because contramap means that we're mapping over the input before we actually do this step. So because we're using the reader module here and the promap instance or method that is implemented there, we have an additional function here, which is run in between these two things. So how's it go? So now that everything is in its place, what happens is the profile comes in, and first we take that profile and we add friend to it. Now, to give you an example, in Xbox, whenever you go in to create your profile, it will add a bunch of numbers to the end of your handle automatically. And I think that this is just so that it avoids duplicates, right? So it might add like some like randomly generated hash set of numbers at the end of your profile. So for instance, mine's Le Monsieur, and their restrictions is that it can be no longer than 12, and I think it's because it also needs to pipe in some randomly generated numbers at the end there. So anyways, we have our profile, and first what we want to do is add this string to it, and then what happens is this f of e to a runs. So we have this, we take the profile, and now we pull off the handle that was supplied. So the value is at hello, which is 1, 2, 3, 4, 5, 6 characters long, and then it pipes through and it adds this. So you have at hello friend 1, 2, 3, 4, 5, 6, 6 plus 6, 12, and we want to check right here on the way out, is the handle greater than or equal to 12. So what ends up happening is this becomes a Boolean in the end. So we have a few different functions in place, and the output of all of that is basically a predicate. So we want to know whether or not the handle within the user's profile is long enough. So what happens down here is we say, hey, is it long enough? And then it's either a yes or a no. So if we come back to our example over here, you can see right here, is it long enough? Yes. If we come back to our code and we shorten this, say at he, come back, you can see it is not long enough, right? And very easily, this is the beauty about these really small and concise functions, is that it's easy to come in and maintain or to change things up. So let's say that you have, a new set of requirements that come in and say, no, we want to make sure that it's no longer than. So we could just say, hey, is this, whoops, we'll go ahead and change this up and say, is this short enough? So we come in to make sure that the predicate's name or the function's name matches the new logic that we're creating. And now what we want to do is check that, let's say it's let's say that it's less than or equal to, I don't know, we'll say 8 characters long. And then you can see down here we're doing the same thing. Is it short enough? If so, yes. If not, no. So we didn't change, or we did. Let's put this back to where it was at hello, and we know that this plus this down here is going to evaluate to 12, and therefore it should not be short enough and it should produce a false. Come back over here. Is handle long enough? We should change this. Is handle short enough? Right. So we change that. Come back over here. All right. Is it short enough? No. So if we come back and let's go ahead and knock off, what is it? 4 characters. Let's go take a look. Yes, it is short enough. So just like that, you already have this really big, really powerful abstraction in place, and you need to come in and change something very quick to come in there and change it. So go ahead and back it back out. Leave it how it was. Yes, like that. And there you have it. This is a profunctor explained as quickly as possible. Alright everyone, that's going to be it for this video. I really appreciate you dropping by. I know that this information was super dense, but trust me, it definitely pays off to understand this type of stuff. And even if you don't use it on a regular day-to-day basis, like for example, full disclosure, I don't always use profunctors, but understanding what they are under the hood, I can reach for them sometimes because I know, I need to map over the input as it's coming in. I know that I can use a Contramap for that. And if I needed to supply a map as well on the way out, then what do? You have a Profunctor implementation. But definitely bimap is used a bit more, and Functor everyone uses every day. So maybe you didn't know these terms before, but functors are just covariant functors, and you use those on a regular basis, especially when you're mapping over regular arrays inside of JavaScript. And then the bimap as well, or the bifunctor, is a part of that covariant family. And then the contramap step is your contravariant functors. So if I spoke too fast on some of this, rewatch it and slow it back down. Take your time. Don't worry if you don't get it all up front. I definitely didn't. It took me a while, and I'm still learning a lot about this. So yeah, the code is available on Git. I've also made a code sandbox, and all of that's going to be linked down below, as well as that article series that I plugged in the beginning from Tom Harding. So yeah, thanks for dropping by, and if you like this material, like, subscribe. It definitely helps me understand if you appreciate this material. So alright everyone, see you.